what happens when an artificial intelligence gets so incredibly capable that humanity literally just runs out of tests hard enough to measure its progress?
Right. It's a fascinating question.
Because, we usually think of machine learning as this like straight line. You give a model a massive data set, it learns the patterns, and boom, it gets smarter.
Yeah, that's a traditional way we look at it.
But right now, we are watching the bleeding edge of AI hit this really massive fundamental wall. The models are devouring data so much faster than we can actually create it. And when it comes to the highest levels of complex problem solving, it's like the human-made textbook is just completely empty.
Completely empty. Yeah, it is really the defining bottleneck of this current AI era.
Yeah.
Because we are demanding that these systems execute incredibly complex, multi-step reasoning over long periods.
Right.
But the high-quality data that you need to actually teach those specific skills, well, it's practically exhausted.
Which brings us to our mission for today's deep dive. We're unpacking a paradigm-shifting framework that essentially allows an AI to realize it has outgrown its human teachers.
Which is wild.
It is. So it just starts building its own curriculum. Today, we are looking at a brand new state-of-the-art research paper dated June 8th, 2026.
Fresh off the presses.
Exactly. It's titled Socratic-SWE, Self-Evolving Coding Agents via Trace-Derived Agent Skills. And I want to note right up front, this is a joint powerhouse effort coming from AI Data at Alibaba Group and Shanghai Jiao Tong University, including their EPIC lab.
Yeah, and it's a remarkable piece of engineering.
Yeah.
Because they aren't just trying to squeeze a little more juice out of existing data sets. They've built an autonomous architecture where the AI meticulously maps its own weaknesses and then generates hyper-targeted problems to force its own evolution.
Okay, to really understand why this is such a massive leap, we have to look at the arena they are working in, which is software engineering, or SWE. Because we aren't just talking about prompting a chatbot to, write a 10-line Python script to sort a grocery list.
Oh, far from it. Software engineering has really emerged as the ultimate crucible for measuring general AI intelligence. Real SWE tasks demand that an agent navigate a live executable environment.
Right, it's messy.
Very messy. It has to search through thousands of files in a massive repository, localize a really subtle bug, manipulate the code, run terminal commands, read error logs, and crucially ensure that fixing one thing doesn't break 3 other things.
Right, the classic developer nightmare. So we know that reinforcement learning is kind of the standard approach here, but why are we hitting a wall? Like if the AI is just exploring the environment and getting feedback, why can't it just keep learning indefinitely?
Well, because reinforcement learning has a fatal dependency. It requires vast amounts of high-quality, diverse tasks to train on.
Which we just said we don't have.
Exactly. Creating a verified, complex software bug and the corresponding solution for it is incredibly time-consuming and expensive for human engineers to do.
So how is the industry dealing with that?
Well, they've turned to synthetic data generation, basically having computers write the tasks. But the current synthetic pipelines are fundamentally flawed.
Flawed how? Are they just generating bad code?
It's not really that the code is bad. It's that the tasks are completely divorced from what the AI actually needs to learn. Existing systems usually rely on, fixed mutation rules.
Okay.
So they blindly inject bugs or delete lines of code at random to create a problem. But those problems act totally independently of what the AI model actually needs to practice to get better.
Okay, let's unpack this. Wait, so we have these supercomputers, these multi-billion parameter models, but they're essentially stuck doing busy work.
Essentially, yes.
It's like, okay, imagine a student who keeps failing algebra, but the teacher just blindly hands them random geometry pop quizzes because that's literally all they have in the filing cabinet. The training doesn't match the actual capability gaps at all.
That is a really highly accurate way to look at it. The generated curriculum is entirely misaligned with the model's internal gaps. But the tragedy of the current paradigm goes even deeper than bad pop quizzes.
Oh, really?
Yeah. The real waste is how current algorithms handle the AI's actual attempts to solve these problems. In the research, this is called a solving trace.
A solving trace. Okay, break that down for me. What does that actually look like inside the system?
So when an AI attempts to fix a repository bug, it leaves a very dense behavioral log. It searches for a file, it reads a function, it tries a bash command, gets a syntax error, realizes its mistake, opens a different file, and maybe runs a test suite.
Right, it's exploring.
Exactly. That entire sequence of actions, decisions, and environmental feedback That is the solving trace. It's this rich map of the model's cognitive process.
It's basically showing its work, like a student's scratch paper.
Yes, exactly. But here's the problem.
Yeah.
Right now, the dominant reinforcement learning algorithms, even the really highly advanced ones like GRPO, they essentially ignore all of that.
Whoa, okay, alphabet soup alert. GRPO.
Oh, apologies. GRPO stands for Group Relative Policy Optimization. It's a very popular algorithm right now for training large language models. But the way it functions in this specific context is that it just looks at the final outcome.
Like, did it pass or fail?
Exactly. Did the code pass the test or fail? It issues a simple scalar reward, basically a 1 or a 0, and then it discards the entire solving trace.
Wait. So it literally takes a test, gets a C-, and instantly throws away the scratch paper where it wrote out all its flawed logic.
That is precisely what happens.
But that's where the actual learning should happen. The AI spends all this computing power generating a detailed log of exactly where its logic went off the rails, and the algorithm just gives it an F and deletes the evidence.
Yeah, the algorithm only reinforces the final outcome, completely ignoring the microscopic steps that led to the failure in the first place. And that is the core insight of the Socratic-SWE paper. They recognize that these discarded traces are not garbage.
They're gold.
They are a direct, unvarnished view into the model's current capability boundary.
Right, because if the AI made a mistake, the trace shows exactly why it made the mistake.
Exactly. The traces are generated by the agent itself, so they perfectly map what the AI struggles with. They reveal recurring failure modes.
Like what?
Like maybe a tendency to misuse a specific library or a habit of writing loops that cause memory leaks. And they also contain the messy, successful strategies that the AI occasionally stumbles upon.
Wow. So the AI's trash is actually this treasure trove of highly personalized curriculum data. It's the ultimate diagnostic tool.
It really is.
And I guess this brings us directly to the architecture they built to exploit this, the Socratic-SWE framework. The paper describes this as a closed-loop self-evolution framework. So how does it actually take a trash log file and turn it into a targeted lesson plan?
It operates on a very elegant 3-stage loop. So the first stage, the AI takes on the role of the solver.
Okay, so
It attempts to fix various software issues, and crucially, the system captures and saves every single solving trace. It leaves the scratch paper on the desk.
got it. Stage 1 is just capturing the raw data.
Right. Then stage 2 is where the magic happens. Instead of trashing those logs, Socratic-SWE introduces a distillation model. In the paper, they utilized Quen 3.627D for this specific task.
Okay.
This distillation model's entire job is to ingest all of those solving traces, both the successes and the failures, and analyze them for recurring patterns.
Okay, I need to pause you there because analyzing for patterns sounds a bit like a black box. How does an LLM actually extract a usable skill from thousands of lines of messy terminal output?
It's actually a highly structured prompting process. The distillation model is instructed to look for very specific behavioral clusters. It looks at a failed trace and asks, what was the intended action? What went wrong? And what is the generalized rule the solver violated?
Oh, okay.
Once it identifies this, it formulates it into an entry in what they call the agent skill registry.
So what does a registry entry actually look like? Is it just a text file that says, like, hey, stop messing up Python dictionaries?
It is far more rigorous than that. The paper provides a brilliant, really concrete example using a repository called OAuthLib, which deals with authentication protocols.
Right, common stuff.
So the distillation model analyzes the solver's failed attempts and notices a highly specific vulnerability. It logs a skill gap related to scope helper contracts.
Scope helper contract sounds dense. What is the actual mistake the AI is making there?
Well, in OAuthLib, when you convert a list into a scope string, the repository has very strict proprietary rules about how that data needs to be filtered.
Okay.
The distillation model sees that the solver keeps applying a generic Python filter instead of the repository's specific rule, which causes a cascade of errors. Or it notices a gap in device endpoint constructor storage.
Wait, what's that one?
That's where the solver repeatedly swaps variables of the exact same type simply because it isn't paying close attention to the specific parameter names.
Oh, okay. That makes total sense. So the registry isn't just a list of bad habits. It's this highly formalized database of the AI's precise contextual blind spots. It documents the trigger condition, the flawed action, and the required behavior.
Exactly. And that structured registry feeds directly into the third stage. Now the AI switches its hat It is no longer the solver, it becomes the generator.
Oh, I see.
It accesses the agent's skill registry, pulls one of those specific weaknesses, like that OAuth-lib variable swapping issue we just talked about, and uses it as a blueprint to synthesize a brand new, targeted practice task.
Wow.
It will deliberately inject a bug into a real repository that requires that exact skill to fix.
Okay, here's where it gets really interesting. The AI is basically playing 4D chess with itself.
It really is.
It's acting as the devious teacher, the generator, who reads the student's mind, locates their microscopic weak spot, and writes a pop quiz specifically designed to trip them up. And then it switches back to the student, the solver, to take the test.
Yeah, it is a continuous system of autonomous coevolution. The solver generates the traces are distilled into structured skills, the skills guide the generator to create new tasks, and then the solver trains on those tasks, producing new, slightly more advanced traces.
So hold on, let me play devil's advocate for a second. If I'm a student writing my own math test, I might accidentally write an equation that is mathematically impossible to solve, right? Or I might write a question that's just absolute gibberish.
That is a very real risk.
Right. If the AI is generating its own curriculum, how do we know the generator isn't polluting the training pool with broken, unsolvable garbage tasks?
That is actually the most critical vulnerability in any self-play architecture.
Yeah.
If the generated tasks are flawed, the model will basically train itself into a state of collapse.
So how do they fix it?
To prevent this, Socratic-SWE relies on an execution-grounded validation pipeline. Think of it as a rigorous, four-step gauntlet that every synthetic task must survive inside an isolated, real-world repository sandbox before it ever reaches the solver.
Oh, a gauntlet. Walk me through it. What are the 4 steps?
Step 1 is format. Is the generated task syntactically valid? Like, did the generator actually output a properly structured JSON or patch file?
Okay, basic sanity check.
Right. If it passes that, it moves to step 2, grounding.
Meaning it has to actually exist in the real world?
Precisely. The
Yeah.
grounding check verifies that the task references files, functions, and variables that actually exist in the target repository.
Mm-hmm.
You cannot ask the solver to fix a bug in a directory that simply doesn't exist.
Makes sense. What's next?
Step 3 is execution. Can the generated test environment actually compile and run without crashing the core infrastructure? Is the test stable across multiple runs?
Okay, so far we've ensured the task is formatted correctly, grounded in reality, and physically runs without breaking the computer. What's the final gate?
Step 4 is semantics. And this is by far the hardest one to pass.
Yeah.
The generated task must actually separate a broken state from a repaired state.
What does that mean in practice?
It means the test suite has to fail when the synthetic bug is present, and it absolutely must pass when the generator's reference fix is applied. If it doesn't meet all 4 criteria, it is instantly discarded.
Okay, so the gauntlet guarantees the test is fair, real, and solvable. But here is my pushback. Valid doesn't mean useful.
How do you mean?
Well, I could write a perfectly valid, grounded, executable test for you on how to print "Hello World" in a terminal. It would pass all 4 gates. But practicing that isn't going to make you a better software engineer.
That's a very fair point.
Or alternatively, I could give you a task so obscure and complex that it takes you a week to solve, but it teaches you absolutely nothing about general coding principles. How does the system know a task is actually driving intelligence upward?
That is exactly the problem the researchers needed to solve next, and it brings us to the most mathematically elegant component of the entire paper, the solver gradient alignment reward.
Okay, you just casually dropped solver gradient alignment. Let's back up. Treat me like I know what a neural network is, but I don't have a PhD in mathematics.
Yeah.
What are we actually aligning here?
Fair enough. Let's talk about how neural networks actually learn. When a model trains on a task, its internal math, its weights and parameters shift slightly.
Right.
That shift is called a gradient. Think of a gradient as a mathematical arrow pointing in a specific direction of learning.
Okay, so a gradient is basically an arrow pointing toward a change in the model's brain.
Exactly. Now, the researchers maintain a small, heavily protected set of 100 trusted, human-verified validation tasks. These are incredibly high-quality, diverse problems.
Okay.
Before the AI trains on any new synthetic task, they measure how its internal gradients would shift if it trained on those 100 trusted tasks.
Oh, I see. So those 100 trusted tasks create like a master arrow, like a compass needle pointing toward true north, the direction of actual verified improvement.
That's a perfect analogy. That master arrow is our true north. Next, the system looks at the brand new synthetic task the generator just created. It calculates the gradient for that specific task.
Right. Which way is the synthetic task's arrow pointing?
Yes. And to figure out if the synthetic task is useful, they use a mathematical function called cosine similarity.
Cosine similarity, break that down for me.
Simply put, cosine similarity is just a way to measure the angle between two arrows. It asks, how closely aligned are these two directions? If the synthetic task's arrow points in the exact same direction as the true north arrow from our human-verified tasks, the cosine similarity is high.
And the generator gets a reward?
It receives a massive reward, yes.
Oh, wow. So if the synthetic task pushes the model's brain in a weird, useless direction, it gets penalized, even if the task was perfectly solvable. This completely decouples the concept of difficulty from the concept of utility.
It does, and the ablation studies in the paper prove why this decoupling is absolutely mandatory.
Let me stop you again. Ablation study. That's when you, turn off a piece of the machine to see what breaks, right?
Yes, exactly. In one ablation study, the researchers removed the gradient alignment entirely and replaced it with a simple hardness reward. They basically told the generator, just make the tasks as difficult as possible. The reward was simply 1 minus the pass rate.
I feel like I know how that ends. Making it harder doesn't make it better.
It was disastrous.
Yeah.
The overall performance of the model actually degraded by 3 full points.
Jeez. It's like a weightlifter trying to lift a 2-ton truck instead of incrementally heavier barbells. The muscle doesn't learn, it just fails completely. The tasks have to be aligned with actual measurable capability gains.
Precisely. If a task is just maximally difficult, the gradient of learning is 0 because the model has no pathway to even understand the solution. The gradient-aligned reward ensures the synthetic curriculum is constantly pulling the model toward genuine improvement, not just tricking it with irrelevant complexity.
Okay, so we have the complete picture now. The solver tries to fix bugs and leaves traces. The distillation model analyzes those traces to populate the AJ skill registry. The generator uses the registry to build hyper-targeted tasks. The gauntlet ensures the tasks are solvable, and cosine similarity ensures the tasks align with true north.
That's the loop.
When you put all of this together and actually turn the machine on, what happens? What were the numbers?
The results are incredibly striking, especially when you consider the constraints they were operating under. They ran this framework with a strict compute budget of just 36,000 training instances generated over 3 iterations.
Wow.
And they used Qwen 3.59b as their base solver model, which is a relatively small model by today's standards.
Yeah, 36,000 instances is tiny. Usually we hear about models training on millions or billions of tokens for months on end.
It is highly constrained. But despite that, Socratic-SWE achieved an astonishing 50.4% pass rate on the SWE bench verified benchmark.
Over 50%. It successfully resolved over half of the real-world verified software engineering issues it was handed. How does that compare to the alternatives out there?
It outperformed the baseline agent by a massive 7.80 points. But the real victory is that it beat the top existing self-playing baseline, a method known as SSR, by 3.4 points.
Yeah.
And crucially, it didn't suffer from early saturation.
What do you mean by early saturation?
Well, other self-play architectures like Spiral or Absolute Zero, they suffer from a phenomenon called mode collapse.
Mode collapse.
Yeah, they might improve for the first iteration or two, but then their task generation loses focus. They start generating repetitive or unhelpful tasks, and the model's performance plateaus or even regresses. Socratic-SWE completely avoided mode collapse. It just kept climbing, iteration after iteration.
Well, because it is continuously refreshing its understanding of its own flaws, it can't collapse if it's always hunting for its newest, most current weakness. And there was another detail in those ablation studies that proves this, wasn't there?
Yes. When the researchers purposefully severed the agent skill registry from the framework, meaning the generator had to create tasks without knowing the solver's specific weaknesses, performance dropped by an enormous 4.2 points.
Which totally confirms that the personalized curriculum, that devious teacher reading the student's mind, is the true engine of this entire framework. But there was one final result in this paper that absolutely blew my mind. They didn't just evaluate this model on fixing software bugs.
Ah, you're referring to the transfer learning results on Terminal Bench 2.0.
Yes. Let's talk about that, because this is where the implications get really massive. Terminal Bench 2.0 isn't about writing code, is it?
No, it is a benchmark designed to test general task completion within a command line interface. It evaluates how well an agent can navigate a Linux terminal, chain different bash commands together, manipulate file structures, and interpret system logs.
So it tests general agentic behavior, not just software repair.
Exactly.
And how did Socratic-SWE do?
The skills it learned completely transferred. And Socratic-SWE improved the model's performance on Terminal Bench 2.0 by 4.50 points compared to the baseline.
So what does this all mean? This is why you need to pay attention to this, regardless of whether you know how to code. The skills this AI learned while trying to fix its own hyper-targeted bugs, like learning how to accurately search a directory structure, how to read a messy test output, how to navigate a live digital environment, they made it a significantly better, smarter general operator.
Yes.
It didn't just become a hyper-specialized bug-fixing machine, it became a more capable digital entity entirely.
That is the core takeaway. If we connect this to the bigger picture, it proves a fundamental truth about learning architectures. Knowledge compounds most effectively when it is applied directly to the friction points of your own ignorance. By utilizing a closed-loop system of continuous, personalized self-improvement, by refusing to throw away the scratch paper, an agent can develop generalizable skills that actually outpace static, human-provided training data.
We started this deep dive looking at a learning landscape that was basically hitting a wall because we couldn't write tests fast enough. And the solution Alibaba and SJTU found was to just stop trying to be the teacher. With Socratic-SWE, the AI distills its own traces, generates its own mathematically aligned curriculum, and continuously evolves out of its own bottlenecks.
It's a massive shift.
But I want to leave you with a final, lingering thought to mull over. We just explored how Socratic-SWE allows an AI to map its own microscopic flaws and generate hyperspecific bugs to teach itself how to fix them. But if this closed loop continues, if the AI is constantly writing its own tests based on the ever-shifting gradients of its own neural pathways, how long until it starts generating agent skills and training tasks that are so alien, so utterly complex that human engineers can no longer even comprehend what the AI is teaching itself?
That's a chilling thought.
Right. When the student becomes the teacher, and the scratch paper is written in a mathematical language we can't even translate, what exactly will it be learning? Thank you for joining us on this deep dive. Keep asking questions and stay curious.